Hello, and welcome to Physics at Night. I'm so glad you found your way here. The world outside is loud. It is full of rush and noise and the constant demand for your attention. But in here, the lights are low. The pace is slow. In here, we have time to ask the questions that usually get lost in the daylight. Tonight, we are going to talk about the most constant companion of your life. We're going to talk about gravity. Right now, you are feeling it. It is the heaviness in your eyelids. It is the pressure of your body against the mattress. It is the invisible blanket that holds you safe. For your entire life, you have thought of gravity as a force, a pull, a tether that ties you to the ground. But tonight, we're going to undo that idea. We're going to peel back the layer of force and reveal the layer of geometry underneath. We're going to discover that the earth is not pulling you down. We're going to learn that you are actually trying to slide and the floor's getting in your way. We're going to see that space is not empty and time is not straight. We're going to learn that gravity is simply the shape of the universe hugging you. It is a beautiful, gentle realization, and I hope that by the end of this story, your weight won't feel like a burden. It will feel like a connection. If you find peace in this quiet corner of the internet, I'd be grateful if you gave this video a gentle like, and if you're comfortable, leave a comment telling me where you're drifting from tonight. It lights up a map of rest across the globe. As always, I am not a doctor. I am just a voice in the dark inviting you to wonder. So, find a comfortable position. Let your shoulders drop. Unclench your jaw. Let the gravity of the earth do the work for you. You don't have to hold on. You are being held. Let's begin. Let's begin by finding our place in the room. I want you to bring your attention to the back of your head. Feel the pillow. Feel the specific texture of the fabric. Feel the way the pillow compresses under the weight of your skull. Now move your attention down to your shoulders. Feel them sinking into the mattress. Move down to your hips, your heels. Feel that heaviness. We call this sensation relaxing. But in the language of physics, something much more active is happening. You are pushing against the earth, and the earth is pushing back. For most of us, gravity is just background noise. It is the most boring force in the universe. It is the reason you drop your phone and the screen cracks. It is the reason your legs get tired when you walk up a hill. It is the reason you can't fly. We resent it. We fight it. We ignore it. But tonight, I want you to look at it with new eyes. I want you to see it not as a nuisance, but as a mystery, a deep, haunting mystery that kept the smartest people in human history awake at night for thousands of years. Think about what is actually happening right now. 4,000 miles beneath your bed, there is the center of the earth, a ball of solid iron spinning in the dark. Between you and that core, there are thousands of miles of rock, magma, water, concrete, and yet, somehow, that core has a grip on you. It is holding you. It is reaching up through the crust, reaching up through the foundation of your building, reaching up through the floorboards, and grabbing every single atom in your body. It is grabbing your skin. It is grabbing your blood. It is grabbing the DNA inside your cells, and it is doing this without touching you. It is doing it instantly. It is doing it silently. How? If I wanted to pull you toward me, I would have to grab your hand. I would need a physical connection, a rope, a chain. If I tried to pull you from across the room by just waving my hands, nothing would happen. I'm not a wizard. I cannot exert force across empty space, but the Earth can. The Sun can. The Earth is 93 million miles away from the Sun. That is a vast, terrifying ocean of nothingness, and yet the Sun holds the Earth on a leash. It swings the Earth around its head like a stone on a string. Where is the string? What is it made of? How does the Earth know the Sun is there? This is the problem of action at a distance. And for a long time, it terrified physicists. Even Isaac Newton, the man who wrote the laws of gravity, didn't understand it. He wrote the equations that described how gravity works, but he refused to guess why it works. He privately admitted that the idea of gravity acting across empty space without a medium was an absurdity. He knew something was missing. He knew there was a ghost in the machine. But the mystery gets deeper when you realize how different gravity is from everything else. Think about the other forces in your life. Think about light. Light is a force. It carries energy. It can push things. But you can hide from light. You can put up a curtain. You can wear a mask. You can build a wall. If you hide in a dark room, the light cannot touch you. Think about magnetism. If you have a powerful magnet, it can pull a piece of metal from across the table. But if you wrap that magnet in a thick layer of lead or steel, the magnetism is blocked. You can shield yourself from it. Think about sound. You can wear earplugs. You can soundproof a room. You can escape the noise. But gravity. Gravity is the only thing in the universe you cannot hide from. There is no gravity shield. You cannot build a room that blocks it. If you built a box made of lead and wrapped it in concrete and buried it under a mountain, the gravity of the moon would still pass right through it. It passes through walls like they are made of smoke. It passes through planets. Neutrinos pass through the Earth without touching anything, and gravity passes through everything without being stopped. It is relentless. It is the silent partner of reality. It is always there. When you are asleep, it is holding you. When you are awake, it is holding you. When you jump in the air, it is waiting for you to come back. It is the force that gathered the dust of the early universe to build the stars. It is the force that crushed the stars to create the elements in your blood. And it is the force that will eventually drag the galaxies back together or let them drift apart at the end of time. It is the Alpha and the Omega, the architect and the undertaker. But tonight, I want to plant a seed of doubt in your mind, a seed that will grow throughout this series. I want you to question the sensation of pull. We are taught that gravity pulls us down. It feels like a pull, doesn't it? If you hold a heavy bag of groceries, you feel the handle pulling down on your fingers. If you hang from a pull-up bar, you feel your body pulling down on your arms. But is that gravity, or is that something else? I want you to imagine a scenario. This is the thought experiment that changed everything for Albert Einstein. Imagine a man painting the roof of a house. Suddenly, he slips. He falls off the roof. Don't worry, in physics thought experiments no one ever gets hurt. He lands in a soft pile of hay. But for the 2 seconds that he is falling, what does he feel? Does he feel heavy? Does he feel the earth pulling him? No. He feels weightless. If he was holding a paintbrush and he let go of it while he was falling, the brush wouldn't fall to his feet. It would float right next to his face. If he pulled a coin out of his pocket and let go, it would hover in the air beside him. For those 2 seconds, gravity seems to have vanished. The man feels exactly like an astronaut floating in deep space. Now, think about that. If gravity is a force that is reaching up and pulling him, Why does the pull disappear just because you let go of the roof? If I tie a rope around your waist and pull you, and you trip and fall, I am still pulling you. You still feel the rope. But with gravity, the moment you surrender to it, the feeling of the force vanishes, the rope disappears. This led Einstein to a terrifying and beautiful conclusion. Maybe, just maybe, gravity is not a force at all. Maybe the pull you feel right now is an illusion. Maybe the earth isn't pulling you down. Maybe the earth is rushing up to hit you. Wait, that sounds wrong. The room isn't moving. The bed isn't moving up like an elevator. So how can the earth be rushing up? This is where we have to change our definition of motion. And this is where the story of spacetime begins. Whatever gravity is, it is not like the other forces. Electromagnetism lives in the universe. Gravity is the universe. Gravity is the shape of the stage itself. So, as you lie there, I want you to rethink your weight. Feel the pressure on your back again. Usually we think, gravity is pulling me down into the bed. But try to flip the image. Try to think, I am trying to float through the universe in a straight line, but this bed keeps getting in my way. The bed is interrupting your fall. The bed is pushing you. The only force acting on you right now is the electromagnetic force of the atoms in the mattress, pushing you up. You are not being pulled down, you are being pushed up. And the heaviness you feel is the inertia of your own body resisting that push. It is a subtle shift, but it changes everything. It means that you are not a static object sitting on a static planet. You are a traveller. You are trying to follow a path through the dark geometry of the cosmos, and the Earth is a giant obstacle in your path. This is the beginning of general relativity. It is the idea that falling is the natural state of all things. To fall is to be free. To stand still is to fight the universe. So, tonight we are going to stop fighting. We are going to let the mind fall. We are going to let the imagination drift. We have opened the door to the mystery. We have realized that the invisible rope of Isaac Newton might not exist. But if there is no rope, what is holding the moon? If there is no rope, why do apples fall? If there is no rope, what is curving the path of the traveller? To answer that, we have to stop looking at the objects, and we have to start looking at the empty space between them. We have to look at the nothing, and we have to realize that the nothing is actually something. In the next chapter, we're going to look at the old map. We're going to pay our respects to the way we used to think. We're going to look at the clockwork universe of the past. Because to understand the revolution, you first have to understand the regime it overthrew. But for now, stay with the sensation, the mystery of the hold, the silent, unblockable, undeniable connection between you and the center of the world. You are anchored, you are safe. We felt the heaviness of our bodies pressing into the mattress. We questioned the invisible force that holds us there. We asked, is it really a pull, or is it something else? But before we can tear down the walls of our perception, we have to look at the house we're living in. We have to look at the story of gravity that we have been telling ourselves for the last 300 years. It is a good story. It is a story of ropes and chains and invisible tethers. It is a story that built the modern world. It allows us to build bridges that don't fall down. It allows us to fire rockets to the moon and land within a few miles of the target. It allows us to predict the exact second of a solar eclipse 1,000 years in the future. This story is the Newtonian universe. And even though we are going to learn that it is technically wrong, it is still the most successful approximation in the history of thought. So tonight, let's step back into the 17th century. Let's step into the mind of Isaac Newton. I want you to imagine a world before physics. Before Newton, the universe was divided into two separate kingdoms. There was the us Earth, and there was the us sky. On Earth, things were messy. Things fell down, things stopped moving, cups broke, fires burned out. The laws of Earth were heavy and chaotic. In the sky, things were perfect. The planets moved in perfect circles, or so they thought. They never stopped. They never slowed down. They shone with divine light. It was believed that the laws of the sky had absolutely nothing to do with the laws of the Earth. Why would they? A rock is a rock. A star is a star. They are different species of reality. But then, the story goes, a young man sat under a tree in Lincolnshire, England. The year was 1666. The Great Plague had shut down the universities, so he was home, bored, staring at the moon. And then, an apple fell. Now, whether the apple actually hit him on the head is a legend, but the thought that followed is real. Newton watched the apple fall to the ground. He saw it accelerate. It started slow, then got faster until it hit the grass. Thud. He knew that for an object to accelerate, a force must pull it. The earth pulled the apple. Then, he looked up at the moon. He saw a giant rock floating in the sky, and he asked the dangerous question, why doesn't the moon fall? Or, even more brilliantly, maybe the moon is falling. He realized that if you throw an apple hard enough and it curves toward the horizon, if you throw it harder, curves further. If you throw it hard enough, the curve of the apple matches the curve of the earth. The apple falls, but the earth curves away underneath it. It falls forever. This was the spark. Newton realized that the force pulling the apple and the force holding the moon were the same force. He reached up and grabbed the heavens, and he tied them to the ground. He unified the cosmos. He said, the laws that govern the fruit in the orchard are the laws that govern the stars in the galaxy. This is the birth of the clockwork universe. And this gives us our standard picture of gravity, the picture that you and I carry around in our heads every day. In this picture, gravity is a force. It is an active agent. It is an invisible tether. I want you to visualize this tether. Imagine the Earth. Now imagine invisible elastic bands stretching out from the center of the planet. Billions of them. One of them is attached to your waist right now. It is pulling you down. Another one is attached to the lamp. Another one is attached to the moon. In Newton's mind, matter calls out to matter. Every object in the universe has a voice, and that voice says, "Come here." The sun has a very loud voice. It shouts across the void to the earth. The earth hears the shout and it is pulled toward the sun. But the earth is moving sideways, so it gets swung around in a circle, like a cowboy spinning a lasso. This view of the universe is incredibly comforting. It is mechanical. It is predictable. It treats the universe like a giant machine, a grandfather clock. The gears turn, the pendulums swing, the weights pull. If you know where the planets are today, you can calculate exactly where they will be in 1,000,000 years. It feels solid. It feels like a universe we can understand. But there is a hidden assumption in this story, a quiet foundation that Newton built his house upon. And that foundation is the nature of the stage itself in Newton's world. Space and time are the stage, and the stage is rigid. Imagine a theatre, the actors, the planets, the stars, you. move around on the stage. They dance, they fight, they orbit. But the stage, the wooden floorboards, the walls, the clock on the wall, they do not participate. In Newton's physics, space is an empty box. It is a 3D grid of infinite straight lines. It is a container. It was there before the stars were born, and it will be there after they die. It is perfectly flat. It is perfectly still. It doesn't care if you put a sun in it, or a black hole, or a feather. Space is just space and time. In Newton's world, time is the master clock. Imagine a single, giant clock ticking somewhere in the background of the universe. Tick, tick, tick. This clock beats the same for everyone. 1 second on Earth is exactly the same as 1 second on Jupiter. 1 second for you standing still is exactly the same as 1 second for you running. Time flows forward like a steady, unchangeable river. This is called absolute space and absolute time. And honestly, this matches our experience, doesn't it? When you walk across your room, the room doesn't change shape. When you sleep, the room doesn't shrink. Space feels solid. And time, we all share the same time. If our watches are synchronized, they stay synchronized. If I go on a trip and come back, I haven't aged less than you. Time feels universal. This is why Newton's gravity is so hard to shake. It aligns perfectly with our human intuition. We live in a flat, steady world. So we invented a flat, steady physics, and for 250 years, nobody questioned it. Why would they? It worked perfectly. Using Newton's math, we found the planet Neptune before we even saw it. We noticed Uranus was wobbling. We used the math of the invisible rope to calculate where the pull was coming from. We pointed a telescope at the empty darkness, and there it was. Neptune. It felt like we had solved the universe. We thought we had the final answer. But there was a ghost. There was a tiny nagging problem that Newton couldn't explain. And it goes back to the question I asked in the intro. How does the Earth know the sun is there? Newton said gravity is a force that acts between two objects, but he also said it acts instantly. Imagine this scenario. Imagine a cosmic wizard snaps his fingers and the sun vanishes. Poof, gone. In Newton's universe, the invisible rope holding the Earth would be cut instantly. The Earth would immediately fly off into the dark. At the exact same moment the sun disappeared, the Earth would lose its orbit. But wait. We know that light takes 8 minutes to travel from the sun to the Earth. So, if the sun vanished, we would still see it shining in the sky for 8 minutes. We would still feel its heat for 8 minutes. We wouldn't know it was gone. So, if Newton is right, gravity travels faster than light. Gravity travels instantly. This means that gravity can send information. The sun is gone faster than the speed of light. This bothered people. It smelled wrong. Action at a distance felt like magic. How can a force jump across empty space with zero delay? And then there was the planet Mercury, the smallest planet, the one closest to the fire. Mercury orbits the sun in a tight, fast loop, but it wasn't behaving. According to Newton's clockwork, Mercury should follow a precise path, but astronomers looked closely, and they saw that Mercury was drifting. It was wobbling. It was arriving at its destination slightly too early, not by much, by a tiny fraction of a degree every century. But in a clockwork universe, a tiny error is a disaster. If the gears are perfect, why is the small gear slipping? They tried to fix it. They invented invisible planets to explain the wobble. They called one Vulcan. But Vulcan wasn't there. The math was failing. The rope was fraying. And this is where we find ourselves tonight, resting in the comfort of the Newtonian bed. It is a comfortable bed. It is stable. It is intuitive. We like the idea that space is a box and time is a river. We like the idea that we're being held by a force we can calculate. But as we drift towards sleep, we have to admit that the story has holes. We have to admit that the force is a placeholder for something we don't understand. We're like people living in a house who believe the lights turn on because of magic. We have mapped the schedule of the lights. We know when they turn on. We know when they turn off, but we haven't found the wires yet. In the next chapter, we're going to look for the wires. We're going to peel back the wallpaper of the universe. We're going to ask why the force model falls apart when things get really big or really fast. We're going to prepare our minds for a shift in perspective, a shift from mechanics to geometry. But for now, be grateful for Isaac Newton. Be grateful for the stability he gave us. Be grateful that your house stays on the ground. Be grateful that the moon stays in the sky. The rope might be an illusion, but it holds us just the same. In the last chapter, we built a fortress. We built the Newtonian universe, the clockwork cosmos. It was a universe of absolute rules. Space was a rigid box. Time was a steady river. And gravity was an invisible rope that connected every object to every other object. It felt solid. It felt reliable. If you are an engineer building a bridge today, you still use Newton's rules. They work. If you're hitting a baseball, Newton is your friend. But tonight, we are going to look for the cracks in the fortress. We're going to find that this comfortable house has a rotten foundation. The problem with Newton's gravity wasn't that it gave the wrong answers. Mostly it gave the right answers. The problem was that it broke the other laws of physics. It was a bully. It refused to play by the rules that the rest of the universe had to follow. And the biggest rule it broke was the speed limit. I want you to imagine the universe as a vast ocean. Now, imagine that you want to send a message across this ocean. Maybe you want to send a letter, or a radio wave, or a beam of light. In the mid-1800s, a physicist named James Clerk Maxwell discovered something profound about this ocean. He discovered that there is a maximum speed for ripples. Nothing, absolutely nothing, can travel faster than light. Light travels at roughly 670 million miles per hour. That is fast, incredibly fast, but it is not infinite. It is finite. It takes time for light to get from the lamp to your eye, a tiny fraction of a second. It takes time for light to get from the sun to the earth, 8 minutes. It takes time for light to cross the galaxy, 100,000 years. This speed limit, let's call it c, is the refresh rate of reality. It is the speed of causality. It means that cause and effect are separated by a delay. If the sun explodes right now, the effect, us burning up, cannot happen until the information travels to us. We have 8 minutes of ignorance. But now, look at Newton's gravity. Look at the invisible rope. Newton's equations don't have time in them. They say that the force depends on mass and distance. That's it. They imply that the connection is instantaneous. Let's go back to our vanishing sun thought experiment. Imagine the cosmic wizard snaps his fingers. The sun disappears. Pop. According to the speed of light rule, we shouldn't know about this for 8 minutes. We should still see the light. We should still feel the warmth. The news hasn't arrived yet. But according to Newton, the rope of gravity snaps instantly. The very millisecond the sun vanishes. The Earth should fly off into deep space. Do you see the contradiction? We would have a planet that is seeing the sun, feeling the sun, orbiting a ghost, but physically flying away from it. We would receive the gravitational message before the visual message. This creates a disaster for physics. If gravity can travel faster than light, it breaks causality. If you can send a signal faster than light, you can theoretically send messages back in time. You could tell your grandfather not to marry your grandmother. The universe dissolves into paradox. Albert Einstein saw this crack in the wall. He sat in his office in Bern, Switzerland, and he sweated over it. He knew that special relativity, the theory of light speed, was true, and he knew that Newton's gravity worked for planets, but they couldn't both be true in their current form. They were like two pieces of a puzzle that almost fit, but overlapped by an inch. He had to choose. Was the universe instant, or was it delayed? He chose the delay. He decided that nothing, not even the heavy hand of gravity, could outrun light. And if that was true, then Newton's rope had to be cut. But if there is no rope, how does the Earth know where to go? If the sun can't pull the Earth instantly, what is it doing? This led Einstein to the second crack in the foundation. The problem of feeling. We talked in Chapter 1 about the man falling off the roof. We talked about how he feels weightless. Einstein called this the happiest thought of my life. Let's expand on this. I want you to step into a new thought experiment. I want you to imagine you are waking up in a small windowless room. It is an elevator car. There are no windows. You can't see outside. You're floating in the middle of the room. Your coffee cup is floating next to you. You feel perfectly weightless. Now, I ask you a question. Where are you? You have two possibilities. Possibility A. You're deep in outer space, far away from any stars or planets. You're floating because there is no gravity. Possibility B. You're inside an elevator shaft on Earth, but the cable has snapped. You're falling toward the basement at 100 miles per hour. You're falling freely. Here is the kicker. There is no experiment you can do inside the box to tell the difference. You can't look outside. If you drop your keys, in space they float. In the falling box they float because they are falling with you. If you push off the wall, in space you drift. In the falling box you drift. The laws of physics inside the box are identical. The experience is identical. Newton would say these are two totally different situations. He would say, in space, there is no force acting on you. In the shaft, there is a giant force, gravity, acting on you. But Einstein looked at it and said, if they feel the same and they act the same, maybe they say hierarchy is the same. Maybe falling is just floating in a different direction. Maybe gravity isn't a force you feel. Maybe gravity is just the path you take when you're left alone. Now, let's flip the box. Imagine you wake up in the same windowless room, but this time you're standing on the floor. You feel heavy. Your legs are working to hold you up. If you drop your keys, they hit the floor. Clang. I ask you again, where are you? Possibility. You're sitting in the elevator on the ground floor on Earth. Gravity is pulling you down. Possibility B. You're in a rocket ship in deep space. The rocket engine is fiery. It is accelerating up at 1g. The floor is rushing up to hit your feet. Again. You cannot tell the difference. If the rocket accelerates smoothly, it feels exactly like gravity. If you drop your keys in the rocket, the floor rushes up and hits them. It looks exactly like falling. Newton says these are different. One is gravity, one is inertia. Einstein says, no, they are the same. This is the SCIA, equivalence principle. It suggests that gravity and acceleration are twins. Actually, they are the same person wearing different hats. And if gravity is just acceleration, then we don't need a magical force that reaches out and grabs things. We just need to understand why the ground is rushing up to meet us. We need to understand why the straight line of the universe seems to curve. So, we have a problem with speed, the sun. We have a problem with identity, the elevator. But we also have a problem with evidence. Sometimes nature just refuses to cooperate with our math. And the biggest rebel in the solar system is the smallest planet, Mercury. Mercury is the closest planet to the Sun. It lives in the deep end of the gravity well. It whips around the Sun at 100,000 miles per hour, and for centuries, astronomers were pulling their hair out watching it. According to Newton's clockwork, Mercury should trace a perfect ellipse. It should follow the same path, over and over, forever. But when they looked closely, they saw that the orbit was shifting. It was rotating. The point where Mercury got closest to the Sun, the perihelion, was moving slightly every year. It was precessing. Like a spirograph drawing that doesn't quite line up, the error was tiny. It was 43 arc seconds per century. That is roughly the width of a human hair seen from a mile away. But in physics, an error is an error. If the theory is perfect, there should be zero error. Astronomers were desperate to save Newton. They said, there must be an invisible planet hidden near the Sun. Its gravity is pulling on Mercury and causing the wobble. They named this invisible planet Vulcan. They spent 50 years looking for it. They pointed their telescopes at the Sun during eclipses. They scanned the twilight. They found nothing. Vulcan wasn't there. The map was wrong. The invisible rope theory was missing something fundamental about how gravity works when things get really heavy and really fast. So, here we are. It is 1905. The fortress of Newton is crumbling. We know that gravity cannot be instant because of light. We know that gravity feels suspiciously like acceleration because of the elevator. And we know that the planets are drifting off the map because of Mercury. We are lost. We need a new map. We need a new way to describe the stage. We need to stop thinking of space as a box and start thinking of it as a fabric. We need to stop thinking of time as a clock and start thinking of it as a dimension. We need to merge them. In the next chapter, we are going to meet the architect of the new world. We're going to walk into the mind of Albert Einstein, and we're going to see how he took these broken pieces and assembled them into the most beautiful theory in the history of science. We're going to learn that the reason Mercury wobbles, and the reason you feel heavy, and the reason the light bends, is because the universe is not flat. The universe is shaped by what is in it. But for now, rest in the mystery of the falling box. Imagine yourself floating in that windowless room, weightless, free. Are you falling? Are you drifting? It doesn't matter. The sensation is peace. We experience the profound confusion of the equivalence principle. We realize that if you close your eyes, you cannot tell the difference between gravity and acceleration. We realize that the invisible rope of Isaac Newton might just be a story we tell ourselves to explain why the floor is rushing up to meet us. But tearing down an old house is easy. Building a new one is hard. And for Albert Einstein, it was agonizing. We tend to think of Einstein as a wizard. We imagine him waking up one morning, messy hair, chalk in hand, and writing down E empty sect before breakfast. But the theory of gravity, general relativity, was not a morning thought. It was a 10-year war. From 1905 to 1915, Einstein walked through the wilderness. He knew Newton was wrong. He knew that gravity couldn't be instant. He knew that space couldn't be rigid. But he didn't have the math to describe what he was seeing in his head. He had to learn entirely new forms of geometry. He had to beg his mathematician friends for help. "Grossman, you must help me or I will go crazy." He was trying to describe a universe that wasn't a box, but a shape that could bend, a shape that could twist. Tonight, we're going to look at the result of that struggle. We're going to step into the mind of the architect. We're going to learn general relativity. But do not be afraid of the name. It sounds heavy. It sounds like a college exam. But at its heart, it is the simplest idea in the history of science. It is a change in perspective. It is the difference between looking at a map and looking at the territory. I want you to imagine two explorers. Let's call them the beetles. These beetles live on a giant white sphere, but they are very small, and they have no concept of up or down. They believe their world is perfectly flat. To them, they are walking on an infinite sheet of paper. Now, imagine these two beetles stand on the equator of the sphere. They stand 1,000 miles apart. They both face strictly north. They check their compasses. They check their protractors. They make absolutely sure that their paths are perfectly parallel. Parallel lines never meet. That is the rule of flat geometry. They begin to walk. They walk north. At first, everything seems normal. They remain 1,000 miles apart, but as they walk, mysterious things start to happen. Without turning, without steering, they start to drift closer together. After a few weeks, they are only 500 miles apart. After a month, they are only 100 miles apart. The beetles are confused. "I didn't turn," shouts one. "I didn't turn either," shouts the other. "There must be a force," they conclude. "There must be a mysterious attraction pulling us together. Let's call it gravity." They invent a force to explain the motion. They write equations for the force. They say, the force gets stronger the closer we get. But we, looking down from the third dimension, we know the truth. There is no force. There is no attraction. There is no invisible rope connecting the beetles. They are simply walking in straight lines on a curved surface. Because the surface is a sphere, the straight lines naturally converge at the North Pole. The beetles are victims of geometry. This is Einstein's revelation. We are the beetles. We look at the Earth orbiting the Sun. We see it curving. We see it circling. We say, there must be a force pulling it. But Einstein says, no, the Earth is trying to go straight. The Earth is trying to move in a straight line through the universe. But the universe itself is curved. The Sun is a heavy object. It has distorted the shape of the space around it. It has created a hill or a valley in the fabric of reality. And the Earth is simply rolling along the contours of that valley. This solves the problem of action at a distance. Remember the vanishing sun. Remember how Newton's gravity had to travel instantly. In Einstein's world, there is no rope to cut. If the sun disappears, the valley has to flatten out. The shape of space has to snap back to flat. But that snapping action takes time. It ripples outward like a wave on a pond. That ripple, a gravitational wave, travels at the speed of light. So, If the sun vanishes, the ripple travels across the solar system for 8 minutes. For 8 minutes, the Earth continues to roll around the valley, because the valley is still there where the Earth is. When the ripple arrives, the space flattens out, and only then does the Earth fly away. Causality is saved. The speed limit is obeyed. Gravity is not a magical connection between two objects. Gravity is a conversation between an object and the space right next to it. Matter tells space how to curve. Space tells matter how to move. It is a local game of telephone. The sun tells the space near it. Curve. That space tells the next layer. Curve. And so on. Until the message reaches us. This is a beautiful, elegant solution. But it requires us to visualize something impossible. The Beatles were walking on a 2D surface that curved into 3D. We're living in 3D space. So, if our space is curving, what is it curving into? Is there a fourth dimension? Yes, but it's not a spatial dimension. It's not hyper up or hyper down. It is time. This is the hardest part to see, but the most important. Gravity is not just the curving of space, it is the curving of time. In fact, for things that move slowly, like us, or like an apple falling, the time curvature is much stronger than the space curvature. Let's go back to the falling apple. Newton says, the Earth pulls the apple down. Einstein says the apple is moving through time. Even if the apple is holding still in your hand, it is hurtling through time. It is moving from now to then. The Earth is a heavy object. It causes time to flow at different speeds, at different heights. Time flows slightly slower near the ground than it does in the tree. The apple wants to go to the place where time is slowest. In the geometry of space-time, the path of least resistance curves toward the slow time. The apple's future tilts downward. So, when you drop the apple, it isn't being pulled. It is simply sliding down the time gradient. It is coasting toward the slower future. This explains why you feel heavy in bed. Your body wants to slide into the slow time, the center of the Earth. The bed prevents you. You're stuck on the slope. This new view, general relativity, passed the test that Newton failed. Remember Mercury? Remember the planet that was wobbling? The one that arrived too early? Newton's math assumed space was flat. But Mercury is close to the Sun. The space there is very curved. The hill is steep. When Einstein plugged the curvature into his equations, the numbers shifted. The geometry of the curved space accounted for the wobble perfectly, exactly 43 arc-seconds per century. Einstein didn't need an invisible planet named Vulcan, he just needed a better map. When he saw the numbers match, he said he felt palpitations of the heart. He knew he had unlocked the code of the cosmos. So, where does this leave us tonight? It leaves us in a universe that is much softer than we thought. We're not living in a rigid box. We're living on a trampoline. Imagine a giant stretched rubber sheet. The sun is a bowling ball sitting in the middle. It makes a deep well. The Earth is a marble rolling around that well. The moon is a tiny bead rolling around the Earth's dimple. And you are a tiny speck of dust, pressing into the fabric, creating your own microscopic dent. You're not separate from the space around you. You are shaping it. Just by existing, just by having mass, you're bending the universe. You're telling the space-time around you to curve. You are pulling on the Earth just as much as the Earth is pulling on you. This connects you to everything. There is no empty space, there is only the fabric, and we are all knots in that fabric. But this brings up a new question. If gravity is just geometry, why is it so weak? Why can a tiny magnet pick up a paperclip against the pull of the entire Earth? And what happens if the curve gets too steep? What happens if the bowling ball gets too heavy? Does the fabric rip? In the next chapter, we're going to look at the fabric itself. We have talked about space and time separately, but Einstein taught us that they are threads in the same cloth. We're going to weave them together. We're going to define space-time. We're going to learn why you can trade space for time and time for space. And we're going to prepare ourselves to see what happens when the geometry breaks. But for now, rest in the curve. Feel the mattress hugging you. That is the shape of your local space-time. It is a comfortable shape. It cradles you. You're not fighting a force, you're resting in a valley. In the last chapter, we watched the walls of the Newtonian universe crumble. We learned that gravity is not a force that reaches out and grabs things. It is a shape. It is the curvature of the universe itself. Matter tells space how to curve. Space tells matter how to move. But this new map leaves us with a difficult question. What exactly is curving? When we think of curving, we think of physical objects. A piece of paper curves, a rubber sheet curves, a mattress curves. These are things made of atoms. They have texture, they have substance. But space? Space is supposed to be nothing. How can nothing curve? And even harder to imagine, how can time curve? How can a second be bent? To understand gravity, we have to stop thinking of space and time as two separate things. We have to stitch them together. We have to create the fabric that Einstein called K. Space-time. Tonight we're going to do that weaving. We're going to learn that you are not a 3D object moving through a 3D world. You are a 4D object sliding through a 4D crystal. I want you to start by thinking about how you perceive the world right now. Close your eyes. You have a very strong sense of key space. You can move left or right. You can move forward or backward. You can move up or down. These are the 3 dimensions of freedom. You can navigate them at will. You can stop. You can turn around. Now, think about time. Time feels totally different. It feels like a current. It drags you from the past, through the present, toward the future. You cannot stop. You cannot turn around. You cannot go left into last week. To our human brains, space is a stage, and time is a river flowing through the stage. They feel like different species of reality. But in 1908, a mathematician named Hermann Minkowski, who was actually one of Einstein's teachers, stood up at a conference and said something radical. He said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He was telling us that our intuition is wrong. Space and time are not different things. They are the same material, viewed from different angles. To see this, let's look at a simple event. Imagine you want to meet a friend for coffee. You send them a text. You say, "Meet me at the cafe on Main Street on the 2nd floor." You have given them 3 coordinates: latitude, Main Street, longitude, the number, and altitude, 2nd floor. But if you don't give them the 4th coordinate, you will never meet. You have to say, at 2:06 p.m., to locate anything in the universe, an event, a star, a meeting, or yourself, you need 4 numbers, 3 of space, 1 of time. You cannot exist in a place without a time, and you cannot exist in a time without a place. Einstein realized that these 4 numbers are interchangeable in a strange way. You can trade some of your motion through space for motion through time, and vice versa. This leads to the most important visualization in relativity. It is the concept of the cosmic speed limit. We know that nothing can travel faster than the speed of light, c. But here is the secret. Everything travels at the speed of light, including you, right now, lying in your bed. But you're not traveling through space, you're traveling through space-time. Imagine you're in a car on a vast flat salt flat. This car has a peculiar feature. The gas pedal is welded to the floor. The engine is locked at maximum RPM. You're always moving at exactly CUN. You cannot slow down. You cannot speed up. But you have a steering wheel. And on this map, the directions are not north and south. The directions are space and time. Right now, lying still, you're steering your car directly north. Time. You're pouring 100% of your speed into the time direction. You're hurtling toward tomorrow at the maximum possible velocity. This is why you age. This is why time feels like it is rushing by. You're colliding with the future at the speed of light. But now, imagine you get up and start walking. You're turning the steering wheel slightly to the east, space. But your total speed is fixed. If you divert some of your speed to the east, you have less speed available for the north. By moving through space, you must slow down your movement through time. This is time dilation. The faster you move through space, the slower you move through time. If you could turn the car 90 degrees and drive purely east, you would be moving through space at the speed of light, and your speed through time would become 0. Your clock would stop. You would be frozen in the now. This is why photons, particles of light, do not experience time. For a photon, the moment it leaves a star and the moment it hits your eye are the same instant. So, space and time are not separate. Buckets. They are a single currency. You're constantly exchanging seconds for meters and meters for seconds. You're a banker of space-time. This implies that the universe is a fabric, a continuous four-dimensional sheet. Usually we call this the block universe. Imagine a loaf of bread. The whole loaf exists at once. You can slice it lengthwise, space. You can slice it widthwise, time. But it's the same dough. Now, let's bring gravity back into this picture. We said in the last chapter that gravity creates curves in the universe. Now we know what is curving. It is not just the distance between things. It is the relationship between space and time. Think about the texture of this fabric. Is it soft? Is it stiff? How hard is it to bend? If you press your hand into a memory foam mattress, it yields easily. If you press your hand into a block of steel, it doesn't move. Space-time is incredibly stiff. It is billions of times stiffer than steel. To make a noticeable dent in space-time, you need a massive amount of energy to matter. Remember, E is re, es tesko. Mass and energy are the same thing. The Earth is a huge ball of rock, 6 sextillion tons, and yet it barely dents the fabric. The curvature of space near Earth is tiny. It is just enough to keep the moon on a leash, and just enough to keep you in bed. But because the fabric is so stiff, the ripples travel fast, and because the fabric is woven of both space and time, when you bend it, you don't just change the distance, you change the clock. This is the key to understanding general relativity. A massive object, like the sun, sits in the fabric. It stretches the space threads, making distances longer. And it stretches the time threads, making clocks tick slower. Gravity is the result of objects trying to navigate this distorted weave. I want you to visualize your own world line again. Imagine your life as a long thread woven into this blanket. When you are asleep, your thread is going straight up the time axis. When you drive a car, your thread tilts slightly sideways. When you're near a heavy object like the Earth, your thread is being pulled into the dent. You're not separate from the blanket. You're a pattern in the blanket. This unity, this oneness of space and time, is the most profound shift in human thinking. Before Einstein, we thought we were actors on a stage. The stage was dead wood. The clock was a machine on the wall. We were the only things that mattered. Now we know that the stage and the clock are alive. They are reacting to us. They are bending around us. And this explains the equivalence principle we talked about in the elevator. Why does falling feel like floating? Because when you fall, you're surrendering to the weave. You're letting your thread follow the natural grain of the fabric. You're taking the path of least resistance through the 4D block. To stand still, to resist the fall, is to fight the fabric. It is to try to force your thread to go straight when the weave wants to curve. That struggle is what you feel as weight. So, tonight, lie in the fabric. Feel the stiffness of it holding you up. Feel the flow of it carrying you toward tomorrow. You're a four-dimensional being. You occupy a volume of space and a duration of time. You're a solid shape in the block universe, and gravity is simply the shape of the room you are in. But describing this fabric is one thing. Seeing how it actually moves things is another. How does a curve make a planet orbit? How does a dent make an apple fall? Why doesn't the apple just sit in the dent? Why does it slide? In the next chapter, we're going to look at the mechanics of the bend. We're going to visualize, really visualize, how a straight line can turn into a circle without any force touching it. We're going to learn how to see the invisible slopes, but for now, be a traveler. Keep your hands on the wheel of your space-time car. You're cruising at the speed of light toward the morning. The road is smooth. The engine is quiet. We wove the threads. We stopped looking at space as a box and time as a clock. We started looking at them as a single continuous fabric called space-time. We learned that you are a four-dimensional traveler. Even when you're lying perfectly still in your bed, you're hurtling through the dimension of time at the speed of light. But tonight, we have to solve a mechanical mystery. We have to answer the question that usually breaks people's brains when they first learn relativity. We know that gravity is a curve in space-time. We know that the Earth creates a dent in the fabric. But how does a dent make an apple fall? Think about it. If I put a bowling ball on a mattress, it creates a dent. If I place a marble next to it, the marble rolls into the dent. That makes sense. But why does the marble roll? Because gravity pulled it down the slope. We are using gravity, the Earth pulling the marble, to explain gravity, the marble rolling. It is a circular argument. If we want to explain gravity without using gravity, we have to look deeper. We have to understand how a curve in geometry can transform into a motion in space. To do this, we need to separate the space bend from the time bend, because they do very different things. Let's start with the easy one. Curved space. I want you to imagine you're a pilot. You're flying a plane from New York to London. You want to save fuel, so you want to fly the shortest possible distance. A straight line. If you look at a flat paper map of the world, a straight line from New York to London goes right across the Atlantic Ocean, east. But if you look at a globe, the shortest path is actually a curve. It goes up north, over Canada, near Greenland, and then down to England. It is called a great circle route. If you fly this path, you keep your steering wheel perfectly straight. You never turn the plane, you just fly straight. But because the Earth is curved beneath you, your path looks curved to someone watching from a satellite. This is exactly how planets orbit. The Earth is the plane. It is flying through the solar system. It is trying to go in a straight line, but the space around the Sun is curved like the globe. So even though the Earth thinks it is going straight, it ends up going in a circle. This explains orbits. Orbits are just straight lines in a curved space. But this doesn't explain the apple. Imagine you are holding an apple in your hand. You let go. It starts to move. It goes from 0 miles per hour to 10 to 20. It accelerates toward the floor. Why? The apple wasn't moving. The airplane analogy requires the object to be moving already. You can't curve a path if you don't have a path. If the apple is stationary in space, why does it suddenly decide to go down? This is where the magic happens. This is where curved time enters the room. We have to remember the secret of the last chapter. The apple is not stationary. It is moving through time, and it is moving fast. It is exploding toward the future at 670 million miles per hour. Now, remember what the Earth does to time. The Earth is a heavy object. It slows down time, but it doesn't slow it down evenly. Gravity gets stronger as you get closer to the center. So, time flows slower near the floor than it does near the ceiling. It is a tiny difference. If you live on the first floor of a building, you age a billionth of a nanosecond less than someone on the top floor. But to the universe, this difference is everything. I want you to visualize the apple again, but don't visualize it as a round fruit. Visualize it as a tiny car with 2 wheels, a left wheel and a right wheel. The car is driving down the highway of time. The left wheel is the part of the apple closer to the ceiling. The right wheel is the part of the apple closer to the floor. Because time moves faster near the ceiling, the left wheel turns faster. Because time moves slower near the floor, the right wheel turns slower. What happens when a car has 1 fast wheel and 1 slow wheel? It turns. It veers toward the slow side. If you're driving down the road and your right tires get stuck in the mud, moving slower, while your left tires are on pavement, moving faster, your car will swerve to the right. This is exactly what is happening to the apple. It is swerving into the future. Its path through space-time is bending toward the slow time zone. And where is the slow time zone? The Earth. So, the apple falls, because its feet are aging slower than its head. The curvature of time rotates the apple's velocity vector. It takes some of that massive speed through time and rotates it into speed through space. This is why gravity is so powerful, even though the curvature is so weak. The Earth only warps time by a tiny, tiny amount. But because the apple is moving through time at the speed of light, that tiny warp gets magnified. A tiny turn at 670 million miles per hour creates a noticeable acceleration, 32 feet per second squared, 9.8 meters per second squared. This is the profound realization of general relativity. Gravity on Earth is almost entirely due to the curvature of time. If only space were curved and time were flat, the apple wouldn't fall. Orbits would look different. The universe would be unrecognizable. It is the warping of the clock that keeps your feet on the ground. So, let's re-examine the feeling of weight one more time. We have been doing this in every chapter, peeling back the layers. Chapter 1. Weight is a mystery. Chapter 2. Weight is a pull. Chapter 3. Weight is acceleration. now. Chapter 6. Weight is a time crash. You're lying in bed. Your body is a traveller hurtling through time, because your back is closer to the earth than your chest. Your back wants to move through time slower than your chest. Your body wants to curve, it wants to swerve downward into the mattress. It wants to follow the natural curve of the Spacetime river. But the mattress is rigid. The mattress refuses to move. So, you're crashing into the mattress, not in space, but in space-time. You're constantly trying to turn into the earth, and the earth is constantly shoving you back onto a straight path. The pressure you feel on your back is the sensation of being forced to travel in an unnatural straight line through a curved universe. You're being straightened out by the bed, and that hurts. That requires force. That is weight. This creates a beautiful, unified picture of the universe. There is no force of gravity. There are just objects trying to follow the path of maximum aging. In physics, this is called the principle of maximal aging. Objects naturally want to go where time is slowest. They want to extend their journey through the moment, and mass, heavy mass, provides that slow lane. So the sun doesn't pull the earth. The sun provides a region of slow time, and the earth, loving the slow lane, curves into it. It is lazy physics. Nature is essentially lazy. It always wants to take the easiest path, and in a curved universe, the easiest path is a curve. We call these paths geodesics. A geodesic is the straightest possible line you can draw on a curved surface. The Great Circle route for the airplane is a geodesic. The orbit of the moon is a geodesic. The fall of the apple is a geodesic. And you, if you rolled out of bed, you would follow a geodesic to the floor. But as long as you stay in bed, you are defying the geodesic. You are a rebel. You're using the electromagnetic strength of the mattress to fight the geometry of the cosmos. So, as you lie there, visualize the river of time flowing through the room. Visualize it flowing slightly faster near the ceiling fan. Visualize it flowing slightly slower near the rug. Visualize the subtle gradient, the invisible slope of the clock. You are surfing that slope. You're riding the wave of time, and gravity is simply the name we give to the surfboard's tilt. It removes the spooky action at a distance. The earth doesn't need to reach out and touch you. The earth just sits there, being heavy and slowing down the time in your bedroom. And you respond to the local time. You respond to the environment right next to your skin. It is local. It is logical. It is continuous. The puzzle pieces fit. But we've been talking a lot about heavy objects. We keep saying the earth curves space. The sun curves time. But how? Why does mass bend the fabric? What is it about a rock that makes the universe warp? And is it only rocks? What about light? What about heat? What about energy? In the next chapter, we're going to look at the other side of the equation. Matter tells space how to curve. We're going to ask, what counts as matter? And we're going to find out that gravity doesn't just come from stuff. It comes from energy, pressure, momentum. It comes from the stress of existence itself. We're going to open the hood of the stress energy tensor, a scary name for a beautiful engine. But for now, rest in the geodesic. You are a time traveller, you're steering toward tomorrow, and the earth is just a gentle bend in the road. We looked at the mechanism of the fall. We learned that gravity is not a force pulling you down. It is a collision between your body, which is hurtling through time, and the earth, which has warped time. You are falling because your feet are moving through time slower than your head. You're swerving into the future. It is a beautiful geometric picture. Matter tells space how to curve. Space tells matter how to move. But tonight, we need to look at the first half of that sentence. Matter tells space how to curve. We've been using the word matter a lot. We talk about rocks and planets and stars, heavy things. We imagine a bowling ball sitting on a trampoline. The heavier the ball, the deeper the dip. This is the intuitive view. Mass creates gravity. But Einstein discovered something deeper. He discovered that mass is just a disguise. Mass is not the only thing that creates gravity. In fact, if you look closely enough, mass doesn't really exist. Tonight, we're going to open the hood of the universe. We're going to look at the engine that actually generates the curvature. It is called the stress energy tensor. I know, that sounds like a piece of scary machinery from a science fiction movie. But I want you to imagine it as a simple box with 10 dials on it. Every point in the universe has one of these boxes, and these dials tell space-time exactly how to bend. Let's look at the first dial. This is the big one, the one we know. Energy density. You might expect this dial to be labelled mass, but remember Einstein's most famous equation, EAGMC, energy equals mass times the speed of light squared. This equation tells us that mass and energy are the same thing. Mass is just super concentrated energy. It is energy frozen in a form we can touch. A rock is just a cage for a tremendous amount of potential energy. So, when the universe asks, how much gravity should I make here? It doesn't count the atoms, it counts the energy. It adds up all the mass energy of the protons and neutrons. It adds up the chemical energy in the bonds. It adds up the thermal energy of the heat. This leads to a strange realization. A hot potato weighs more than a cold potato. Why? Because the hot potato has more thermal energy. The atoms are vibrating faster. That kinetic energy counts. It creates a tiny bit of extra gravity. If you put a hot potato on a sensitive enough scale and let it cool down, the scale would drop, the gravity would weaken. Now, for a potato, the difference is unmeasurably small. But for a star, or the universe right after the Big Bang, the heat is heavy. The heat creates gravity. So, gravity is not just about stuff, it is about activity. Anything that has energy bends space. Now, let's look at the other dials on the machine. Because it turns out, energy isn't the only thing that bends the fabric. There is another source of gravity that is hidden in plain sight. Pressure. Imagine a spring. If you leave the spring loose, it has a certain mass. It creates a certain amount of gravity. Now, compress the spring, squeeze it tight, clamp it down. Does it weigh more? Yes. You've added energy to the system, potential energy in the coiled metal. But you have also created pressure inside the material. In Einstein's equations, pressure itself is a source of gravity. If you have a balloon filled with gas, and you squeeze it, you are increasing the pressure. That pressure actually pulls on the fabric of space-time. It says to the universe, curve more. Think about the Earth beneath you. The core of the Earth is under immense pressure, millions of atmospheres. That squeezing force actually contributes to the gravity you feel right now. A significant portion of the Earth's gravitational pull comes not just from the iron atoms, but from the fact that the iron atoms are being crushed. This stress in the material creates the curve in the space. That is why it is called the stress energy tensor. Now, let's do a thought experiment to see just how weird this gets. Let's talk about light. Does light have mass? No. Photons are massless particles. So, does light create gravity? In Newton's world, the answer is no. Newton says gravity is a force between two masses. If mass is zero, gravity is zero. F for G M2 send R to lol. 0 times anything is 0. So to Newton, a flashlight beam is invisible to gravity. But in Einstein's world, the answer is yes, because light has energy, and energy bends space. Imagine you have a box. The box is lined with perfect mirrors on the inside. The box is empty. It sits on a scale. It weighs 1 pound. Now, you turn on a flashlight and fill the box with light. Then you quickly close the lid. The light bounces back and forth inside, trapped forever. Does the box weigh more? Yes. The energy of the trapped light adds to the total energy of the system. The box creates a deeper dent in space-time. If you fill the box with enough light, it would weigh as much as a rock. If you filled it with too much light, it would eventually collapse into a black hole made entirely of light. This is called a Kugelblitz. So, gravity is truly universal. It doesn't care if you're a rock, a gas, a beam of light, or a squeezed spring. If you exist, and you have energy, you're bending the cosmos. But this leads us to the most mind-bending dial of all, the dial called self-interaction. This is where the math gets hard, but the concept is beautiful. We know that mass creates gravity, and we know that gravity is a field of energy, gravitational potential energy. So, does the energy of the gravity itself create more gravity? Yes. Gravity weighs something. The energy contained in the gravitational field of the Earth creates its own tiny gravitational field, and that tiny field creates a tinier field. It is an infinite loop. Gravity breeding gravity. For the Earth, this effect is small. But for a black hole, a huge amount of the gravity of a black hole comes from the gravity itself. The energy of the curvature is so intense that it curves the space further. It is a self-sustaining storm of geometry. This is why Einstein's equations are so hard to solve. They are non-linear. In Newton's world, if you have two suns, you just add their gravity together. Simple addition. 1 plus 1, 2. In Einstein's world, 1 plus 1. 2 is 1. The sum is greater than the parts, because the interaction between them adds extra weight. So, we have this machine, the stress-energy tensor. It takes mass, energy, pressure, heat, momentum, and strain, puts them in a blender, and outputs curvature. But there is one final question we have to ask tonight. Why is the machine so inefficient? Think about the Earth again. It is massive. 6 sextillion tons. It is huge. And yet, you can lift your arm. A tiny biological machine can defeat the entire Earth just by raising your hand. A tiny fridge magnet can pick up a paperclip against the entire pull of the planet. Gravity is incredibly weak. It is the weakest force in the universe by far. The electromagnetic force is trillions of times stronger. Why? If mass tells space to curve, why is space so hard to curve? The answer lies in the stiffness of space-time. I want you to imagine the fabric of the universe again. Is it like a soft rubber sheet? No. If it were soft, your body would create a deep pit. You would attract objects from across the room. The fact that you don't have a noticeable gravitational pull means the sheet is stiff. How stiff? Imagine a sheet of steel. Now imagine a sheet of diamond. Now multiply that stiffness by 1 billion. Space-time is the stiffest material in existence. It effectively has a modulus of elasticity that is off the charts. It wants to stay flat. It hates to bend. To make even a tiny microscopic dent in it, you need a concentrated ball of energy the size of a planet. To make a dent deep enough to trap light, a black hole, you need to crush a star. This conversion factor, the stiffness of the universe, is written in Einstein's equation as 8pg(c)(4) because seqal, the speed of light, is a huge number, and it is in the denominator at the bottom of the fraction, and it is to the fourth power. The resulting number is vanishingly small. This is a good thing. If space-time were soft, the universe would be chaotic. Planets would crash into each other constantly. Your body would collapse under its own gravity. The universe would crumple up like a piece of paper. The stiffness protects us. It keeps the solar system stable. It allows us to move freely without getting stuck to the walls. So, as you lie there, appreciate the rigidity of the vacuum. You are resting in a structure that is stronger than steel, yet invisible as a ghost. The Earth has managed to bend it just enough to hold you, just enough to keep the atmosphere from floating away, but not enough to crush you. We are living in the Goldilocks zone of curvature. So, we have built the stage. We know what the fabric is, space-time. We know what bends it, energy and pressure. We know why we slide, time dilation. But now we need to look at the actors. We need to watch things move through this curved world. We need to watch comets and light beams and clocks moving through the valley. In the next chapter, we're going to talk about the path. We're going to learn why objects orbit in ellipses. We're going to learn why light bends around the sun. And we're going to learn that straight is a relative term. For now, feel the pressure of your own energy, the heat of your body, the mass of your atoms. You're a tiny source of gravity. You're bending the universe just a little bit right here in this room. You are pulling on the Earth, and the Earth is pulling on you. You're not just an observer, you are a participant. In the last chapter, we looked under the hood. We opened the stress-energy tensor and saw the engine of gravity. We learned that mass, energy, pressure, and even light itself are all bending the fabric of space-time. We learned that the universe is incredibly stiff, stiffer than diamond, which is why it takes a planet to create a comfortable gravity well. But tonight, we are going to leave the engine room. We're going to go out onto the track. We have built the curved stage. Now, we need to watch the dancers. We're going to answer the question that has fascinated humans since the first time a shepherd looked up at the night sky. Why do things orbit? Why does the moon circle the Earth? Why does the Earth circle the sun? Why doesn't everything just fly off into the dark or crash into the middle? To understand this, we have to unlearn a habit. We have to stop thinking of an orbit as a tether. Remember Newton's invisible rope. The cowboy spinning the lasso cut the rope. In Einstein's world, objects are not being pulled. They are simply trying to do the one thing all objects want to do: go straight. This is the law of inertia. An object in motion stays in motion, in a straight line, unless acted upon by a force. But Einstein says there is no force. So, the Earth is going straight, the moon is going straight, the apple is going straight. But how can a circle be a straight line? This brings us to the concept of the geodesic. A geodesic is the generalized definition of straight. On a flat piece of paper, a straight line is, well, straight. It's the shortest distance between 2 points. But on a curved surface, the shortest distance is a curve. I want you to imagine you are walking on the surface of a giant sphere, like the Earth. You start at the equator. You walk north. You do not turn left. You do not turn right. You keep your feet perfectly aligned. Eventually, you will cross the North Pole. go down the other side and come back to the equator, you have walked in a circle. But at every single step you are walking straight. This is exactly what the Earth is doing around the Sun. The Earth is flying through the 4D fabric of space-time. It is trying to go straight ahead. But the Sun has created a deep valley in the fabric. The straightest path through that valley happens to be a spiral, or, in 3D space, an ellipse. So, an orbit is not a struggle. It is not a fight between centrifugal force and gravity. It is the path of least resistance. It is the planet surrendering to the shape of the room. But why do some things orbit while other things crash? Why does the apple hit the ground, but the moon stays up? This brings us to the delicate balance of velocity. I want you to imagine the space funnel again. Imagine a large plastic funnel, like the ones used for coin donations at museums. You roll a coin into it. If you just drop the coin, it falls straight to the bottom. Plink. This is the apple. The apple has almost no horizontal speed. It moves through time, falling toward the future, but it has no sideways motion in space. So, the curvature of time dominates. It swerves into the slow time zone, the ground, immediately. But what if you flick the coin? What if you give it some sideways speed? Now, the coin enters the funnel moving fast. It starts to fall toward the hole, but its sideways momentum carries it around the curve. If you flick it just right, it finds a sweet spot. It circles the hole. It doesn't fall in. It doesn't fly out. It stays at the same height, going round and round. This is an orbit. But in relativity, we describe it differently. We say that the object is trading space curvature against time curvature. Remember, the Earth curves both space, the distance, and time, the clock. For a fast-moving object like a satellite, the spatial curvature becomes important. The satellite is moving so fast across the spatial bumps that it counters the time slide. Think of it like a race car on a banked track. If the car goes too slow, it slides down the bank to the infield. If the car goes too fast, it climbs up the bank and flies off the track. If the car goes at exactly the right speed, it sticks to the curve perfectly. The gravity of the Earth provides the banked track. The speed of the satellite determines its lane, and this explains a beautiful mystery. Weightlessness in orbit. Look at the astronauts on the International Space Station. They are floating. Why? Is it because there is no gravity up there? No. The space station is only 250 miles up. The gravity there is 90% as strong as it is on the ground. If you built a 250-mile tall tower and stood on top of it, you would feel heavy. You would not float. So why do the astronauts float? Because they are falling. The space station is falling toward the Earth at 17,000 miles per hour, but because it is moving sideways so fast, it misses the Earth. The Earth curves away underneath it. It is falling around the planet. And because they are falling, they are following the geodesic perfectly. They are surrendering to the geometry. Remember our rule. If you surrender to gravity, you feel weightless. They are not fighting the curve, so they don't feel the weight. So, an orbit is simply a forever fall. It is a state of perpetual surrender. Now, let's look at something even faster. Let's look at light. In Newton's world, a comet orbits the sun because it is heavy, but light has no mass. So Newton predicted that light should travel in a perfectly straight line. If a star is behind the sun, we shouldn't be able to see it. The sun should block it. But Einstein said, light has to follow the geodesic too. The road is curved, The car, light, has to turn. He predicted that if you looked at the sun during a total eclipse when the glare is blocked, you would see stars right next to the edge of the sun. But those stars aren't really there. They're actually behind the sun. The light from those stars passed near the sun and fell into the valley. It curved around the sun and came to our eyes. The sun acted like a giant glass lens. This is called gravitational lensing. In 1919, an astronomer named Arthur Eddington went to an island off the coast of Africa to test this. He waited for the eclipse. The sky went dark. The stars appeared. He took a photo. He measured the position of the stars, and they were shifted. They were shifted by exactly the amount Einstein predicted. The news went around the world. Lights all askew in the heavens. Newton overthrown. It was the moment humanity realized that space is not empty. It is a lens. But there is one final strange path we need to talk about. The path that doesn't just curve, but twists. In Chapter 5, we talked about how space-time is a fabric. But imagine grabbing a tablecloth in the middle and twisting it. The fabric ripples and rotates. This happens in space too. The Earth is spinning, and because the Earth is dragging the fabric along with it, the space around Earth is slowly twisting. This is called frame dragging. Imagine a satellite orbiting the Earth over the poles. It thinks it is going in a perfect north-south loop, but over time, the loop gets dragged. The orbit itself rotates, like a spinning top that precesses. We actually measured this. NASA launched a mission called Gravity Probe B. It carried the most perfect spheres ever made by humans, quartz gyroscopes. They put them in orbit and watched them for years, and sure enough, the gyroscopes drifted. They were dragged by the twisting fabric of space. So, not only is space curved, like a bowl, it is swirling, like a drain. You're living in a whirlpool. So, what does this mean for you tonight? It means that stillness is an illusion. Even if you lie perfectly still, you are on a planet that is orbiting. The planet is on a geodesic around the sun. The sun is on a geodesic around the center of the galaxy. The galaxy is falling toward the great attractor. Everything is falling. Everything is rolling down the slopes of the invisible hills. We're all travelers on curved roads, and gravity is just the traffic rules of those roads. It tells us which way the curve goes. But what happens when the road ends? What happens when the curve gets so steep that the path becomes a trap? What happens when the hill becomes a cliff? In the next chapter, we are going to look at the extreme end of the spectrum. We're going to unify the gentle gravity of the Earth with the crushing gravity of a black hole. We're going to see that they are the same phenomenon, just turned up to volume 11. We're going to see what happens when the fabric rips. But for now, float in your orbit. Imagine your bed is a capsule. You are falling around the center of the Earth. You're weightless in your mind. Even if your body feels the sheets, you're following the curve. We watched objects dancing in the dark. We saw satellites falling around the Earth. We saw light bending around the sun. We saw that an orbit is not a struggle against a force, but a surrender to a curve. It is the forever fall, but tonight we are going to push the curve to its limit. We are going to take the gentle valley of the Earth and deepen it. We are going to turn the dial of gravity all the way to the right. We are going to find that gravity is universal. The same set of rules that keeps your feet on the floor is the same set of rules that crushes stars into nothingness. It is one continuous arc, from the apple to the black hole. I want you to imagine a slider, like a volume knob for curvature. Level 1. The asteroid. Imagine a rock in space 10 miles wide. It has mass, it has gravity. If you stood on it, you would weigh almost nothing. If you jumped, you would drift up for 10 minutes before slowly floating back down. Here, the fabric of space-time is almost flat. It is like a sheet with a tiny pebble on it. The time dilation is negligible. Your watch ticks at exactly the same speed as a watch in deep space. Level 2, the Earth. Now slide the knob up. We have the Earth, 8,000 miles wide. The fabric is stiffer here. The dip is noticeable. If you jump, you come back down in 1 second. The time dilation is real, but tiny. Your feet are younger than your head by a fraction of a second over a lifetime. This is the comfort zone of gravity. It holds us, but it doesn't crush us. Level 3. The Sun. Slide the knob further. The Sun is 330,000 times heavier than Earth. The dip in the fabric is deep. It is a canyon. Light passing by bends noticeably. Time slows down significantly. If you lived on the surface of the Sun and didn't burn up, your clock would run about a minute slower per year compared to Earth. This is heavy gravity. But now, let's enter the danger zone. Let's see what happens when we squeeze matter too tight. Level 4. The White Dwarf. Imagine we take the Sun and we let it die. It runs out of fuel, the fire goes out, the outward push stops, gravity wins, the star collapses. It shrinks from 1,000,000 miles wide to the size of the Earth. But it keeps all its mass. This is a white dwarf. The density is insane. A teaspoon weighs a ton. The curvature here is sharp. If you dropped a rock from a height of 1 meter, it would hit the ground in a microsecond. Time is dragging. Level 5. The neutron star. Squeeze it harder, crush the atoms until the electrons are forced into the protons. The whole star becomes a city-sized ball of neutrons. It is only 10 miles wide, but it weighs more than the Sun. This is the steepest hill in the universe that you can still, theoretically, stand on. The escape velocity is half the speed of light. If you look sideways, you can see the back of your own head, because the light is orbiting the star. Time is running at 70% speed. If you spent an hour here, an hour and a half would pass on Earth. The fabric of space-time is stretched almost to the breaking point. And finally, Level 6. The Black Hole. Slide the knob to the maximum. Squeeze the neutron star just a little bit more. The structure fails. The neutrons give up. The star collapses to a point. The fabric rips. The dip becomes a bottomless pit. The hill becomes a cliff. The escape velocity hits the speed of light. And time stops. This is the beauty of Einstein's theory. It connects the gentle apple to the monstrous whole. They are not different things. They are just different steepnesses of the same slope. But there is a specific feature of black holes that reveals the true nature of gravity. It is the event horizon. In Newton's world, escape is always possible. If the Earth was super heavy, you just need a bigger rocket. If you have a powerful enough engine, you can blast away from anything, you can fight the force. But in Einstein's world, gravity is not a force, it is geometry, and geometry has rules that cannot be broken by engines. Imagine the river again. Gravity is the river of space flowing into the hole. Near the Earth, the river is slow. You can swim upstream easily. Near the Sun, the river is fast. You need a boat. Near a black hole, the river accelerates to the speed of light. At the event horizon, the space itself is falling inward at the speed of light. Since nothing can swim faster than light, you cannot swim upstream. No matter how powerful your rocket is, you're moving backward. This changes the definition of down. On Earth, down is a direction toward the center, but you can choose to go up. Inside a black hole, the geometry twists so violently that down becomes the future. The center of the hole is no longer a place in space, it is a moment in time. Tuesday is the singularity. You cannot use a rocket to avoid Tuesday. You cannot turn the steering wheel to avoid the future. Gravity has transformed from a pull into a destiny. This is why black holes are so terrifying, but also so serene. They represent the ultimate victory of the curve. The straight line has been bent into a circle and then bent into a knot. But I want you to step back from the edge. We don't need to stay in the danger zone. Let's zoom out to the solar system again. Think about the invisible web that connects all these levels. The sun is at the middle, creating a deep well. The Earth is rolling around the rim. The moon is rolling around the Earth's rim, and you are rolling around the Earth's center. It is a hierarchy of bowls, bowls within bowls within bowls, and this web is surprisingly shaky. In Newton's world, the orbits were fixed forever, but in Einstein's world, moving through space-time creates ripples, gravitational waves. Imagine two black holes orbiting each other. They are heavy, they are fast. As they spin, they drag the fabric of the universe with them. They churn the ocean of space-time. They send out waves, like ripples on a pond. These waves carry energy away. Because the black holes are losing energy, they spiral closer together, they get faster, the waves get louder, until, boom, they collide. In 2015, we heard this collision for the first time. The LIGO Observatory detected a ripple in the fabric of space that passed through the Earth. It came from two black holes colliding 1 billion light-years away. For a fraction of a second, the length of your arm stretched by a tiny, tiny amount. The Earth itself rang like a bell. This proved it once and for all. Space is not a stage. Space is a substance. It can ring. It can wobble. It can carry sound, gravitational sound. We are floating in a dynamic, active ocean. Gravity is just the name we give to the waves and the currents. So, look at the room around you tonight. It looks stable, but it is ringing with the echoes of distant collisions. It is bent by the mass of the Earth. It is twisted by the rotation of the planet. You're not sitting in an empty box. You're sitting in a complex, beautiful, four-dimensional sculpture, and you are part of the sculpture. Your mass is adding a tiny detail to the shape of the room. We've travelled a long way in this series. We started with a question about weight. We tore down the invisible rope. We built a fabric of space and time. We watched apples slide down the time gradient. And now we have stood on the edge of the abyss. We have unified the universe, from the falling dust mote to the colliding star. It is all just geometry, but there is one final chapter. We need to come back home. We need to take all this cosmic machinery, all this talk of tensors and warps, and bring it back to the pillow. We need to ask, what does this mean for my sleep? We need to find the peace in the physics, because understanding the universe shouldn't make us feel small and scared. It should make us feel held. In the final chapter, we're going to reflect on this curved reality. We're going to let the mind relax into the knowledge that we are supported by the very shape of existence. We're going to find stillness in the motion. So, let the black holes fade into the distance. Let the neutron stars cool down. Let's drift back to the gentle green valley of the earth. You are safe here. The gravity is just right. Let's drift to the last part. We've arrived at the end of our journey. We've travelled a long way together tonight. We started right here, in this room, with a simple question about the weight of your body against the mattress. We asked, what is holding me down? And to answer that question, we had to tear down the universe we thought we knew. We had to cut the invisible ropes of Isaac Newton. We had to shatter the glass box of absolute space. We had to stop the steady ticking of the universal clock. We climbed into the mind of Albert Einstein. We stood in the falling elevator and learned that falling is just floating. We drove the car across the salt flats of Spacetime and learned that gravity is just aging. We peered under the hood of the stress energy tensor and saw that energy, heat and pressure are the hands that mould the clay of the cosmos. And finally we stood on the edge of a black hole and watched the river of space flow into the dark. But now it is time to come home. It is time to leave the extreme edges of physics and return to the gentle, quiet reality of your bedroom. I want you to take a deep breath. Inhale the stillness of the room. Exhale the complexity of the math. Feel the bed underneath you one last time, but feel it differently now. Before tonight, you might have felt that the earth was pulling you. You might have felt that you were a heavy object being dragged down by a relentless force, a burden, a weight. But now, I hope you feel something else. I hope you feel the connection. The pressure on your back is not a punishment. It is a conversation. It is the earth communicating with you through the language of geometry. The planet is massive. It has bent the fabric of time around it, and your body, a traveller made of stardust, is responding to that bend. You're trying to slide into the future along the path of least resistance. You're trying to follow the curve, and the earth is gently catching you. The floor is rising up to meet you, moment by moment, keeping you safe, keeping you here. This new perspective changes our place in the universe. In the old Newtonian world, we were objects placed into a container. We were actors on a dead stage. We were separate from the stars. We were lonely. But in Einstein's world, there is no container. There is only the fabric. We're not in the universe. We are the universe. We are ripples in the cloth. We are knots in the weave. Just by lying there, you are bending the cosmos. It is a tiny amount, yes, but it is real. Your mass is telling the space around you to curve. Your heat is adding to the energy of the field. You're pulling on the earth just as much as the earth is pulling on you. You're pulling on the moon, you're pulling on the sun, you're pulling on the most distant galaxy in the observable universe. The web of gravity connects everything to everything else. It is the nervous system of reality. And you are a neuron in that system. You are not an observer watching the show. You are a participant. So, let the anxiety of separation fade away. You cannot fall off the earth. You cannot be lost in the void. You are stitched into the fabric. You belong here. And reflect on the stability of it all. We talked about how stiff the universe is. We talked about how hard it is to bend space. Be grateful for that stiffness. If space were soft, the floor would warp under your feet, the walls would buckle, the solar system would be a chaotic mess of colliding planets. But because space-time is rigid, because it is stronger than diamond, we have stability. We have orbits that last for billions of years. We have a sun that stays at a safe distance. We have a reliable down. The universe is built to last. It cradles us in the Goldilocks zone of curvature. not so flat that we float away, not so curved that we are crushed, just right. Now, think about the motion. We often feel like we are standing still, especially at night. The house is quiet, the street is empty, the world feels paused, but we know now that stillness is an illusion. Even as you sleep, you are on a spaceship. The Earth is spinning at 1,000 miles per hour. It is orbiting the Sun at 67,000 miles per hour. The Sun is circling the galaxy at 500,000 miles per hour, and you are riding the geodesic. You are surfing the invisible waves of gravity. You don't have to steer. You don't have to worry about the path. The geometry of the universe has already mapped it out for you. For 4.5 billion years, the Earth has followed this track without fail. It will follow it tomorrow, and the day after. You can trust the path. You can trust the fall. So, as your eyes get heavy, let's do one final visualization. I want you to imagine the timeline of your night. Imagine your sleep not as a pause in your life, but as a journey through the fourth dimension. You're about to travel 8 hours into the future. You are going to close your eyes here and open them in the morning sunlight. During those 8 hours, your body will be resting in space, but your mind will be moving through time. You're going to slide up the vertical axis of your world line. You're going to drift along the river of time, carried by the current. Gravity will watch over you. It will keep your blood flowing. It will keep your blankets on the bed. It will keep the air in the room. It is the silent guardian. It asks for nothing. It requires no fuel. It needs no maintenance. It is simply the shape of home. So, surrender to it. Stop fighting the mattress. Let your muscles go. Let your bones settle. Accept the hug. You have learned the secret of the stars. You have looked behind the curtain of reality. And you have found that there are no gears. There are no ropes. There is only the smooth, silent, elegant curve of existence. The universe is not a machine. It is a thought. It is a shape. And tonight, that shape is a cradle. Thank you for traveling with me. Thank you for wondering. And thank you for trusting the dark. Physics is done for the night. The equations are solved. The variables are balanced. The only thing left to do is to drift. Drift along the geodesic. Drift into the singularity of sleep. Good night.